In this presentation, we're going to have a look at value iteration as well as optimal policies. So we have already learned in the prior presentation that we live in a pretty small world, right? 3x4 grid or 4x3 grid. We have an agent, it explores its world, there are final big rewards, there are immediate small rewards, there are walls, we can fall off the edge of the world. However, as you may know, things don't always work out the way we would like them to work out or we plan. So we're going to add a little bit of a kink to our simple world. We're going to add a stochastic transition model. So here's the idea. Here is the particular one that we're going to be using. You can use other ones. And so in our model, if we plan to go in a certain direction, like in this example, go up, with 80% probability, we're going to end up in the next square that is above this. However, with 10%, we're going to end up in the square to the left, and with 10% in the square to the right. So again, this holds for all directions. So with 80% probability, we end up in the direction we want to go, with 10% to the left, with 10% to the right, except we obviously cannot go into walls, and we cannot fall off the edge of the world because that just isn't right. So that's our stochastic transition function. So now, based on this thing, we will eventually be able to develop optimal policies. We have already seen an optimal policy for the situation where the reward is minus 0.04. I already mentioned to you that, I point out this one over here, this error, which is sort of puzzling. Well, all shall be revealed today. So we're going to be looking at two things: policies, how to read them off, and then value function, utility functions, how to calculate them. So let's stay with policies for a little bit. So here is something. I don't know why the share shows up. Let me see whether I can get rid of this thing. I will see whether I can get rid of that thing after I post this slide. So this is a right arrow over here. So look at this policy. What do you think the reward function is for the individual steps so that we have this policy? So I'm going to let you think about this for a moment. And I'm going to point out this arrow over here, which kind of seems suicidal. So what do you think? Well, oh yes, here's another suicidal one, right? This one says, go this way. It could go up too, I guess. So this policy here, the reward for each of the step, obviously based on these two R, must be less than minus 1. So suppose the reward for making a step is minus 1.1, right? Actually minus 0.2 at the very least. Then obviously we will take this one over here rather than sort of like going up this way and then this way, right? Same thing over here. Let me get out of this nightmarish world that we exist in, where the final rewards are just so small compared to the negative rewards that we take to do a step, right? So as you can tell, what you should learn from this thing is that yes, the rewards do affect our policy. We just want to get out of here in this particular example. Let's have a look at this one over here. Again, now, did you think about this thing? This one means, oh, whatever you want. You can go up this way, this way, this way, this way. I don't care. Just have a good time. Hang out for a while. So what might be the rewards for these states over here that we have? We don't even want to take the reward of plus 1. We can sort of like realize that I don't want to take minus 1. Why wouldn't we even take plus 1? All right, assuming that you thought about this thing for a little bit, if not, pause it and think some more. The reward is positive. So suppose it's a reward of 0.01, right? So in this case, the more we mosey about, the more rewards we accumulate. So actually leaving the world is not a good idea because, well, we can get many, many more rewards by simply going on back and forth, hang out for a while, drink some coffee, hang out, chat a little bit, hey, say hello to some friends, hang out with some other people, go over here. So we're just sort of like going on over here and here. We just sort of like accumulate rewards well beyond plus 1. So again, giving you a sense that the rewards of the individual states has a huge impact on the policy that we eventually develop. All right, so how do we then develop policy? So suppose we have calculated utilities for each state, and how we do that we will see in a moment. So how do we read off a policy? So I already mentioned to you before, if we look at this one over here, it appears that, oh yeah, this one here is much better than this one, so we should go up. But if we look at this one over here, this one is actually higher. So why do we not go up? Why do we go to the left? So that is because, remember, we now have a stochastic transition function. And so just because we intend to go up this way, it doesn't necessarily mean that we end up over here. And so that's what we're going to explore next. This, so to speak, oddity, if you wish. All right, so how do we calculate a policy from a value matrix? So here's our value matrix. And then what we're going to do for each state, we're going to look at the 4 possible actions. So we're going to calculate the action for this state over here. So we can go up, we can go down, we can go left, we can go right. I know that we can go left because there's a wall in the way, but we're sort of like, in principle, are able to do all 4 actions, and we will consider all 4 actions. Don't worry, we won't go to the left. So what we're going to do, let me explain this formula over here. So for each action, say up, that's the one we're going to calculate. Given our transition model, with 80% probability, we're actually going to end up over here. With 10% probability, we're going to end up over here. And with 10% probability, we try to go to the left, but we won't because there's a wall, so we're going to simply stay put. So these are the probabilities given a certain state, this one over here, and an action going up. What's the probability that we're going to end up in this state over here? Okay, so 0.8. What's the utility of the state? 0.762. What's the probability that given the action go up in this state, we're going to end up over here? 0.1%, right? 10%. That's that we're going to end up over here. And the utility of this one is 0.655. So we're going to add that thing into it. And then 0.10 about trying to go left but staying put. So this is simply for the action of going up. And we have to do the same thing for down, left, and right. So what we're going to do is we're going to calculate this summation over here for all 4 actions. So again, each of these summations in our example has 3 terms that we're going to sum together. But notice over here, we're going to do argmax. So among all the actions that are available to us, again, 4 different actions, we're going to look at the action that gives us the highest value over here. And that's the one that we're going to take. So presumably go up. All right, so what we need to do then is for the up action, given our transition function, we have to calculate this summation. So notice that, the probability that we are going to be in state 1, 2, given that we're in state 1, 1 and want to go up, multiply, this is the 0.8, times that utility. That's the first term, okay? So then, again, these pieces are always the same. We're in state 1, 1, we want to go up. Okay, state 1, 1, want to go up. But we may end up in state 1, 2. We may end up in state 1, 1. And we may end up in state 1, 2. Sorry about that. And so we're going to take those utilities. So we're going to calculate that. All right. Again, this transition function, this one over here. And so the probability of, see the beauty of cut and paste, of going up is 0.8, or that we're actually going up when we're trying to go up is 0.8, going left 0.1, going right 0.1. And so these are the values over here. So you multiply this stuff, you sum it all up, ta-da, gives us 0.7456. So now we need to calculate the values for the 3 remaining actions, down, left, and right. And so I have a worksheet over here where I would like you to do that. It is this one over here. Oopsie. Yeah, that's correct. And so please calculate down, left, and right. And when you're done, so pause the video here for a moment, and when you're done, we'll go back. All right, so assuming you're back, you should have come up with these sorts of values here, 0.69, 0.71, 67.6707. So, so those are the sums of all the possible actions that we can do in state A, given our transition function, our probabilistic transition function, and the one that gives the highest value is up. So what we're going to do then is we're going to put up in here. And you might want to calculate the same one for this one over here and see why we go left. So that's how we do that. Now that's how we calculate the policy from a value or utility matrix. Great. So why do I do that before we do calculate the utility matrix? Well, you'll see in a minute. So here's how you actually calculate iteratively a utility matrix. So you're given something like this. Whoopsie. Come on. Well, we'll go back to it here in a minute. You're given something like this. I'm sorry. Notice that what we have over here is we have these final rewards over here, and then we have the step rewards. And what you want to do, though, is you want to calculate the utility matrix, the one that we have seen before, this one over here. And so we're going to do this iteratively by repeatedly updating each of these cells over here that are either not walls or that are not terminal states. That's what we want to do. Okay, so let me go back a little bit here. So here's how we will calculate the utility. So notice that this one over here we have seen before. We again look at our stochastic transition function, except this time we don't take argmax. We're going to take the maximum value that we're actually going to get from this thing among all the actions that are possible, available to us. We will then use a tuning factor, and I'll explain that thing at a later date, that sort of like biases future rewards against immediate rewards. And so the idea is a greedy person might simply only look at the immediate rewards, grab them, and move on. And somebody may, so like a long term thinker might sort of say, oh no, there's this huge reward there at the end of the rainbow. And I really want to get there. And so they might, so like buyers, the future award much, much higher than the immediate reward. So that's what this tuning factor is. For now, I'm simply going to ask you to use 0.9 for it. And again, at a later time, we sort of explore what the thing will do for us. Now notice we also have to add the current reward to it, which typically is negative. So this gives us the utility of a state. All right, so that's what I explained over here. So the idea then is, let's sort of like see whether we can calculate the utility for this state over here. Again, this is the first iteration, and I mean, this is the given information, and we want to sort of update this value over here. As you know already, and as you can imagine, it should be considerably higher than minus 0.04, because, well, it's right next to a really good terminating state or accepting states. Again, we use 0.9 for our tuning factor gamma. So as I mentioned, I have another sheet, and so I ask you to do that to calculate this thing. So please do that now and pause the video for a moment. So assuming that you have calculated the utility for this state over here, I should be consistent, then we will, you should have gotten the following. So utility of 3.33 is minus 0.04 plus the tuning factor times the max of these things over here. And so as it turns out, this should give you a value of 0.6728. And that's what you would put into this cell. And you then obviously calculate utilities in parallel. So for this, and all the other ones. So you take this information, you create a second matrix, and you calculate the matrix based on this information, and then you copy that second matrix on the first one, you continue on. So here's the algorithm that we're going to be using. So we have a utility matrix, we have the maximum change delta, and so what we're going to do for each state in S, we calculate the next utility based on the current utility. So again, this one here is the one that it comes with, the initialized one. So we simply copy it over, and eventually we'll see how this thing works. So this stuff here that I highlighted is this formula that we already explored. So you should be comfortable with this thing. So what we do this for each state. So for each state, we calculate this thing. And then over here is the termination condition. We sort of like say, you know, well, what's the maximum change in utility that we experience, and we save this. And then once the maximum change goes beyond a certain value, we terminate this loop, okay? But if we don't terminate it, then notice we calculate U prime, the second matrix, we copy it into U, and then we calculate the values based on U. So that's very important that you realize that we need to have two matrices to calculate this function, because we do these things, so to speak, in parallel, right? We don't base it on the new values, we base it on the old values. All right, so again, we explained this in quite some detail. There's a for loop, ta-da, a repeat loop, ta-da, and a return. Wow, that is very impressive. So that's one of the things that I'm going to be asking you to do as part of the last programming assignment. So what I want to do next is I want to demo some code here that you can also download that sort of gives you a sense about how these values that we calculated sort of like move from this one over here. So they sort of propagate, right? The goodness and the negativeness. So what I have is on the website, I linked up this code to the value iteration animation. And you can find it over here. And these people are very reputable. Obviously, it's an applet that obviously doesn't work anymore in any of the browsers. So you can simply download the code. It's 2 pieces of Java code. I've downloaded them a long time ago and never had a problem with my checking or savings account since. And so I know about Pool and Macworth. I think I communicate at least with one of them at some point in time. So they're very trustworthy. So hopefully nobody hacked their website, and so you can just download this stuff and play with it a little bit. So here is what you will get if you were to download and install it in Eclipse. Again, you should know these 4 arrows, which means, just do whatever you want to do. I don't care. Discount rate is 0.9. Again, we explore the thing in a little bit more detail. And here are the utilities currently. So we start out with no information at all. So let's do one step. All right, so look at this. Ta-da! This is an accepting state, obviously a very high one with 10. This is an accepting state of -10, not so good. Accepting state of -5, an accepting state of 3. All right. So, so these are the initial values. We discovered them. So let's do another step. So here you see that the goodness of this state is being propagated. So over here we have now a value of 6.29, a value of 617, a value of 628, 63. So this information has propagated. we want to do that. Notice also we do display a couple of things over here. So green gives you a sense of the information being propagated out. The numbers are the current values of the value matrix, and the arrows are the optimal policy based on the current value. So over here we have no information. Over here, you know, we don't want to go left, don't want to go down, want to go right, don't want to go up. Same thing over here. Over here, yes, you know, certainly go into these states, not bad at all. So eventually, as the information propagates between these two, we'll sort of like see how this all works. So let's do another step. Okay, so notice that it propagates out. The value should get higher. Let's look at this one here, 617, 728. So let's see what happens with these two values over here, whether they change. Well, this one already goes down. Let's see where this one eventually goes down. It does. Okay. So as the values go up, the green stuff sort of like propagates out. And again, there are many changes here. Notice that the policy at this point in time doesn't really have any options except for these accepting states. And this one you get out of here. Again, the values don't change very much. Certainly the policy didn't change recently. So there you have it. So that's how this thing works. So again, two things at the same time. We calculate the value matrix, so in white the data, the numbers as the value matrix, and then the blue is the policy based on the current value matrix, and then the green shows you visually the goodness of all these states. All right, so feel free to play around with this thing a little bit. I will talk to you later. Bye.